Hey team, Filip from HIIT Science from the rainy Gold Coast Aquatic Center, and I'm bringing you here today because we're going to chat about the priming effect based on the findings from Bernie et al. 2002. So what we have here is the oxygen consumption on the y-axis in liters per minute, and on the x-axis we have time. So the study that Burnley and al. Conducted in 2002 involved a group of cyclists that did a protocol of 2 times 6 minutes interspersed with 12 minutes of recovery at it was 75% between the second lactate threshold and VO2 max power, which would be about 90% of the power corresponding to VO2 max. So if you were following the last week's lecture or you've seen the recent post about the intensity domains, this would correspond to our severe domain, that is above the critical velocity or power. Meaning that our metabolism does not stabilize, but the oxygen consumption keeps on increasing until it reaches VO2 max. So what we have here are 2 curves representing oxygen consumption, in blue from the first bout and in the black from the second bout. Obviously, these curves represent the group averages. So that's just not one individual. These are the averages from the group that participate in the study. And as you can see, there is a marked difference in the trajectories of these curves. So for the first bout, it took 3 minutes and 30 seconds to reach VO2 max. We also call this time T to VO2 max. While for the second bout, it was over 2 minutes faster. So the T to VO2 max was 1 minute 20 seconds. So now what we should talk about is why this happened. Why second bout of the very same exercise led to a much faster increase in oxygen consumption, which has an implication for our high intensity interval training. So when we look at the curves of the oxygen consumption, we can identify different stages of how the oxygen consumption rises as we begin to exercise, and we call it VO2 kinetics. And this VO2 kinetics can be broken down into several components. So oxygen consumption for a given time, T, can be calculated as the oxygen consumption at the baseline. So this is how Burnley and colleagues, this is how they calculated the baseline. Participants were just sitting for 2 minutes on the exercise bike without pedaling, and this is how we got our baseline. So then the oxygen consumption can be broken down as baseline, amplitude A of the cardiometabolic component, which is the part when the oxygen in our venous blood does not change, but that's a topic for another day, multiplied by maths. I didn't want to complicate this for now. The amplitude of the primary component P, or the fast component. So if we were to look at on our curves here, this is the fast component, this part, for the second bout and for the first bout. Okay? And then we have the amplitude of the slow component S, which we could draw up here. Again, the drawing is not perfect, but this is just for the illustration purposes. So this is how we calculate our oxygen consumption for a given time. This is how we break down these VO2 kinetics. So this is what Burnley et al. Basically did in this study. They calculated and compared the amplitudes, so the size from the bottom to the top, of each component of the oxygen kinetics. So this would be the amplitude of the slow component here. This would be the amplitude of the slow component here. This would be the amplitude of the fast component here. And this would be the amplitude of the fast component here. So I hope you can get what I mean by amplitude. It's the size of the response. And this is what Burnley et al. Basically did in this study. They calculated the amplitudes for each component of the oxygen consumption, and they compare them. So let's look at the numbers. So the size of the primary or the fast component in the first bout, so remember the one that took longer to reach the VO2 max, was 2.11 liters per minute. But then in the second bout, it was 2.44 liters per minute, which was significantly larger. So this tells us, and you can kind of see it from the graph, that the size of the fast response was larger in the second bout compared to the first bout of exercise. And the amplitude or the size of the slow component in the first bout was on average 0.79 liters per minute, but for the second bout it was nearly twice as small. It was 0.4 liters per minute, which was significantly smaller. And then if we go to my beautiful graph again, you can kind of see that the first bout slow component amplitude is much smaller than the size of the slow component in the first bout, where it took much longer to reach the VO2 max. So what I want you to appreciate is that the end oxygen consumption was basically the same. It was 3.69 in the first bout and 3.67 liters per minute after the second bout, at the end of the second bout. So we did not change the end response, the total VO2. We changed the way how we arrive at this total oxygen consumption response. Okay, so everything is cool. We changed the way that oxygen consumption increases at the onset of exercise. But we don't really know why. And here's the answer. So Burnley et al., they recorded the muscle recruitment using the electromyography of the leg muscles. And they expressed it as the percentage of baseline. And the baseline was pedaling against zero load. And they observed that for the first bout, the recruitment was 499% relative to baseline. And for the second bout, the recruitment was 604% relative to baseline muscular activity, which was significantly larger. So what this figure tells us is that the participants activated more muscle fibers during the second bout when they achieved their VO2 max faster. But what's particularly important about this figure is that EMG was recorded during the first 2 minutes of the exercise. So they did not just record more muscle fibers, but they recruited them much faster. And what Burnley et al. Did next, they divided or normalized the amplitude, so the size of the primary response of that fast component relative to the EMG, so the muscular recruitment. And what they seen was basically no difference. So P is the number of the statistical significance, and 0.45 basically tells us that there is no difference between one group and the other. So the one group being the first bout and the other group being the second bout. So this tells us that the faster oxygen kinetics during the second bout were due to the faster muscular recruitment. So what can we do about all of this knowledge of priming effect? You might remember from last week that we talked about the T90, or time above the 90% of VO2 max, as the key target in our HIIT training. If we want to increase our VO2 max, we want to spend as much time as possible at that level, at that intensity. Having learned about the oxygen kinetics, we know that when we do our interval training, we increase our oxygen consumption with the fast component if we exercise above the intensity corresponding to VO2 max. And then when we rest, our oxygen consumption falls down a bit. Then we spike it again with another bout of work, and then it goes down again. Spike it up, and then it goes down again as we get closer and closer to 90% of VO2 max. But now that we know about the priming effect, we can appreciate that there are two key factors to perfecting our HIIT training. So it's the time above 90% of VO2 max, but it's also the time it takes us to get there, to get close to VO2 max. So if we want to speed up the time it takes us to get to the high VO2 max levels, we should do a prior bout at severe intensity that is above the critical velocity or power. We should do a high intensity warm-up if we want to maximize our HIIT training. If you didn't make it to the end of the lecture, that's okay. The lifeguard girl decided to leave the chair and stand in the rain instead of listening to me. So I'll see you next time.